this lesson, we'll simplify radical expressions and add, subtract, multiply, and divide radical expressions. How do radical expressions apply to falling objects? The amount of time t in seconds that it takes for an object to drop d feet is given by t equals the square root of 2d over g, where g equals 32 feet per second squared is the acceleration due to gravity. In this lesson, you'll learn how to simplify radical expressions like the square root of 2d over g. You can use the commutative property in the definition of square root to find an equivalent expression for the product of radicals, such as the square root of 3 times the square root of 5. Begin by squaring the product. So we've got square root of 3 and square root of 5 are both doubled. Squaring, you're taking something times itself. And commutative property, that is rearranged it, so the square root of 3 and the square root of 5 are together. Square root of 3 times square root of 3 is square root of 9, which is 3. Square root of 5 times square root of 5. Square root and squaring are inverse operations. They undo each other, so it's 5. 3 times 5 is 15. Since square root of 3 times square root of 5 is greater than 0, and square root of 3 times square root of 5 equals 15, the square root of 3 times the square root of 5 is the principal square root. That is, square root of 3 times square root of 5 equals the square root of 15. This illustrates the following property of radicals. For any real numbers a and b, and any integer where n is greater than 1, if n is even and a and b are both non-negative, then the nth root of ab equals the nth root of a times the nth root of b, and if n is odd, then the nth root of ab equals the nth root of a times the nth root of b. Follow these steps to simplify a square root. First, factor the radicand into as many squares as possible. Then, use the product property to isolate the perfect squares. And then, third step, simplify each radical. Okay, first step, factor the radicand into as many squares as possible. Hey, 25 is already a perfect square. A to the 4th is a perfect square. B to the 9th we can rewrite as b to the 8th times b. Square root of 25 is 5. The square root of a to the 4th is a squared. The square root of b to the 8th is b to the 4th. And we're left with a square root of b. Now it happens to be that both of our exponents started off as even, so we don't need to use an absolute value this time. Look at a radical that involves division to see if there's a quotient property for radicals similar to the product property. Consider 49 over 9. The radicand is a perfect square, so the square root of 49 over 9 equals the square root of 7 over 3 squared, or 7/3. Notice that 7/3 equals the square root of 49 over the square root of 9. This suggests the following property. For any real numbers a and b, where b does not equal 0, and any integer n greater than 1, the nth root of a over b equals the nth root of a over the nth root of b if all roots are defined. For example, the square root of 27 over the square root of 3 equals the square root of 9, which is 3. A radical expression is in simplified form when the following conditions are met. The index n is as small as possible. The radicand contains no factors other than 1 that are nth powers of an integer or polynomial. The radicand contains no fractions, and no radicals appear in the denominator. To eliminate radicals from a denominator or fractions from a radicand, you can use a process called rationalizing the denominator. To rationalize the denominator, multiply the numerator denominator by a quantity so the radicand has an exact root. You may want to think of rationalizing the denominator as making the denominator a rational number. To simplify, I can see that first the numerator is already a happy perfect square because it's even. The denominator, I can rewrite that as x to the 6th times x. And then the square root of y to the 8th, well, just for a second here, we could rewrite that as y to the 4th squared. And x to the 6th, we could rewrite that as x cubed squared. So you can see that square root and squaring undo each other. So I'm going to have y to the 4th over x cubed, but then I'm still stuck with the square root of x. to get rid of the square root of x, we're going to multiply by square root of x over square root of x. Anything divided by itself is 1, even square root of x's. So I still have my happy little y to the 4th that was happy as it was, but now it's multiplied by square root of x, because when we multiply fractions, we're just multiplying straight across. And square root of x times square root of x is going to be square root of x squared, which of course is just going to be plain old x. So x cubed times x, I wouldn't normally write all this out, I'm just showing it this once, would be x to the 4th. I don't have a radical in the denominator, everything is now simplified. I'm going to start this one the same way as we did the last one by writing it as a quotient. So we have the cube root of 2 over the cube root of, okay, I'm going to rewrite that 9 as 3 squared because I want to point out I want to get the cube root of something cubed. So in order to get that, I'm going to need another factor of 3 and 2 more factors of x. And of course, whatever I do the denominator, I have to do the numerator to keep it equivalent. So now we're going to have the cube root of 2 times 3 is 6, x squared over the cube root of 3 cubed, x cubed, which is what we're trying to get there. So the numerator is the cube root of 6x squared over the cube root of 3 cubed is 3, and the cube root of x cubed is x. And just double checking that we met what we were supposed to do, the index n is as small as possible. The radicand contains no factors other than 1 that are nth integers of the polynomial. No radicand contains no fractions. There's still a fraction in our expression, but it's not in the radical sign. And no radicals appear in the denominator. Those two kind of say similar things. I guess that's important. To simplify, I don't have a number in front of the radical here, so I guess I could just think of that as a 1. So I'm just going to multiply 5 times 1 is 5, and then multiply the things under the radical. So 100 times 10 is 1,000, and a squared times a is a cubed, which both happen to be, happy for us, perfect cubes, because 10 cubed is 1,000. So the cube root of 10 cubed is just 10, and the cube root of a cubed is a, so 5 times 10 is 50, and we have an a. Two radical expressions are called like radical expressions if both the indices and the radicands are alike. Some examples of like and unlike radical expressions are given below. Square root of 3 and cube root of 3 are not like expressions because they have different indices. Indices is plural of index. Fourth root of 5x and fourth root of 5 are not like expressions because the radicands are different. 2 fourth root of 3a and 5 fourth root of 3a are like expressions. The radicands are 3a and the indices are both 4. So in this case, I could add or subtract the coefficients. I could simplify this expression by rewriting the square root of 45 as square root of 9 times square root of 5. And 80 would be square root of 16 square root of 5. And 20 square root of 4 times square root of 5. Square root of 9 is 3. Square root of 16 is 4. Square root of 4 is 2. And then 3 times 3 is 9. 5 times 4 is 20. 4 times 2 is 8. And then if I just add my coefficients, 9 minus 20 is negative 11, plus 8 is negative 3. And they're all times square root of 5. We're going to simplify this expression by using the FOIL method. So 2 times 3 is 6, square root of 3. 2 times negative 1 is negative 2, square root of 3 times square root of 3 is square root of 9. Plus 3 times 3 is 9, square root of 5. And then positive times negative is negative 3, square root of 15. Well, I know what the square root of 9 is. We can simplify that. Square root of 9 is 3, so copy everything else down. And I don't appear to have any like terms. So my final answer is just going to be 6 square root of 3 minus 9 plus 9 square root of 5 minus 3 square root of 15. Now, the order on this would not matter. If you had switched two terms around, it would be equivalent. Again, we're going to FOIL to simplify. So 4 times 4 is 16. Square root of 2 times square root of 2 is square root of 4. Positive times negative is negative. 4 times 7 is 28. Square root of 2. And 4 times 7 is 28. Square root of 2. And positive times negative is negative. 7 times 7 is 49. Happens to be my middle two terms are like terms and they're opposites. So I have 16 times square root of 4 is 2 plus nothing minus 49. I'm not going to have a radical at all in this one. So 32 minus 49 is just negative 17, and we are done. Binomials like those in example 5b of the form a squared of b plus c squared of d and a squared of b minus c squared of d, where a, b, c, and d are rational numbers, are called conjugates of each other. The product of conjugates is always a rational number. You can use conjugates to rationalize denominators. So to simplify this, I'm going to multiply by the conjugate of the denominator. So instead of 4 minus square root of 3, I'm going to multiply by 4 plus square root of 3. And we have to do the same thing to the numerator as denominator. So it's like we're multiplying by 1 and doesn't change the value of the expression. And we're going to FOIL. So 2 times 4 is 8 plus 2 square root of 3 plus 4 square root of 3 plus square root of 9 over 4 times 4 is 16 plus 4 square root of 3, and here comes the magic, minus 4 square root of 3 minus square root of 9. Well, square root of 2 square root of 3 plus 4 square root of 3 would be 6 square root of 3. And square root of 9 we know is 3 over, opposites cancel out, so all I have in the denominator is 16 minus square root of 9 is 3. So 8 plus 3 is 11 plus 6 square root of 3 over 16 minus 3 is 13. We have simplified the expression because we no longer have a radical in the denominator. For any real numbers a and b and any integer n greater than 1, the nth root of a times b equals the nth root of a times the nth root of b, and the nth root of a over b equals the nth root of a over the nth root of b.